Okay, 2.48, we are given a half infinite square well that looks something like this, where everything to the left of x equals 0 is v equals infinity. And then this bottom point of the well is equal to negative 32 h bar squared over ma squared. And then this top thing is v equals 0. Everything, so this is x equals to a. So we have a well from 0 to a, and then it's v equal to 0 everywhere else. And then in part A, we're asked how many bound states are there. So to find bound states, we have to start by finding the Schrodinger equation, or solving the Schrodinger equation. So the general x-dependent solution is going to be equal to d2 psi by dx squared is equal to 2m over h bar squared multiplied by v subtracted by e multiplied by psi. And this is equivalent when x is greater than 0. When x is less than 0, we just have psi equals to 0 because it's infinite everywhere to the left, so it doesn't matter there. So our two solutions, or our two equations that we have to deal with, I'm going to write these in red, are going to be, let's see, d2 psi by dx squared is equal to 2m divided by h bar squared, and this is negative, and I'm actually going to move the negative out so I can move everything inside to become a positive. So this is going to be 32 h bar squared over m a squared plus e multiplied by psi. And then for x being greater than a, v is just equal to 0. So over there we have d2 psi by dx squared is equal to negative 2m over h bar squared times the negative e, right? So in that case, oh, sorry, my apologies. It's positive over here. So 2m over h bar squared times negative e. And we just have to solve both of these. So let's consider whether these constants are positive or not. Because remember, the general method for solving this is to take both of these and sort of make them as d2 psi by dx squared is equal to, you know, L squared psi, and then here d2 psi by dx squared is equal to k squared psi, where sort of the whole point is to just get it in this form. So first off, let's look at this, and we can recognize that immediately energy is always going to be negative, but in order for it to be a bound state, it can't be more negative than 32 h bar squared over ma squared. So this term is always positive. In contrast, we have a negative term here, so this resulting term is negative. We're going to have to add a negative at the front because, you know, we can't put the negative into the L squared, since the L squared is going to, that's going to imply that there's going to be a negative in the square root, which is not possible. Same thing here. E is always negative, so this negative cancels out with the negative that's inherent in the E. So because of that, this entire thing is going to be positive. So we don't have to add a negative in front of the k squared. This whole thing is just positive on its own. The negative that exists here gets absorbed into the E and cancels out and becomes a positive. So these are, in reality, our two solutions. And we solve them as we've always done, which is that for the inside of the well, we solve via a sinusoid. So psi of x is going to equal a piecewise. From 0 to a is going to be a sinusoid, as we've solved all these times before with the infinite and finite square wells. C1 cosine Lx plus, and you know what? Instead of using C1, C2, C3, I'm just going to write A, B, C, D, because that's just easier for me. A cosine Lx plus B sine Lx. And then, so this is when x is between 0 and a. And then when x is greater than a, we have this, which is just a exponential function. So we get ce to the negative kx plus de to the kx when x is greater than a. And our two constants are equivalent to k being equal to the square root of negative 2me over h bar. And then L is being equal to the square root of 2m times 2m over h bar squared times 32 h bar squared over m a squared plus e. Okay, at this point now, we can start solving this and trying to find, because remember, our goal is to find the number of bound states, and to find the number of bound states, we need to find the energy, or the valid values of energy. So we're trying to solve these equations in terms of k. So the first thing we have to do is try to get rid of all these constants at the front via boundary conditions. So the first thing we have is sort of the requirement that there's an infinite wall to the left. So psi of 0 automatically has to equal 0. And if we look, psi of 0 is going to be a cosine of 0 plus b sine of 0. Well, sine of 0 is already just equal to 0. So we have a cosine of 0. Cosine of 0 is going to give us 1. So this implies that a has to equal 0. The next thing we need is that we also need the bound state wave function to go to 0 at positive infinity. Because remember, if we look at this, obviously there's going to be some psi of 0 is going to equal to 0 right here, and our wave function is going to look something like, it's going to travel like this, and then it's going to reach the sort of the wall, and it's going to exponentially decay this way, and eventually it's going to sort of the big point here is that psi has to go to 0 as x goes to infinity, and if we look at this, the solution that modulates psi as x goes to infinity is this bottom one. And if we let d be non-zero, then this term is going to blow up to infinity as psi goes to infinity. And that's just not allowed because that's going to give us a non-normalizable wave function. So by requirement, we also need d to equal 0. So my apologies, I just realized this is supposed to be a is equal to 0. So a is equal to 0 and d equals to 0, or d is equal to 0. So our new wave function solution is going to look like a much simpler piecewise that's easier to deal with. B sine of Lx when x is between 0 and a, and then c times e to the negative kx when x is greater than a. So far, this is stuff that we've done many times before via previous problems and previous sections. The next thing we're going to do now is going to enforce continuity, because that's the other boundary condition we can enforce. So the wave function has to be continuous at x equals to a. This potential is not infinite as well. This is a finite wall. So because of that, the derivative also has to be continuous. So let's enforce that now. Let's do this in green. So we have also let's write out the derivative of psi as well. So that's going to give us b times L cosine of Lx when x is between 0 and a. And then we have negative ck e to the negative kx when x is greater than a. So if we enforce continuity of both the wave function and its derivative at x equals to a, then we get b times sine of La has to equal c times e at negative ka. And then we have b times L cosine of La has to equal negative ck e to the negative ka. And at this point, we can actually cancel out the b's and c's, because we can divide this bottom term underneath the top term. So what I mean by that is if I divide the left side by bl cosine La and the right side by ce negative ka, then I can cancel out the constants, and I can get b sine of La over bl times cosine of La is equal to ce to the negative ka divided by negative ck e to the negative ka. Once again, this is just a standard method that we've done many times before when solving these kinds of problems. So look back on the sections talking about sort of the finite square well and whatnot if you're not familiar with how this is being worked. In fact, this is actually the exact steps we're taking to solve the finite square well back in that section. So read that section if you're not familiar with what's happening here, or if you're not comfortable with what's happening here. The b's cancel out. The ce to the negative ka cancels with the ce to the negative ka. So we get sine of La is equal to L cosine of La. And I'm going to move the negative k at the bottom to this side. So negative k sine La is equal to L cosine of La. And now we have the same situation that we had originally in the book, in the section itself, when we were actually solving for the finite square well for the first time, which is that we have a transcendental equation, and it's in terms of two different variables, k and L. So to find the valid energies, we're going to have to rewrite this purely in terms of one variable. And we're going to use the exact same technique that the book used, which is we're going to start by saying, okay, I know what k and l are equal to. K is equal to the square root of negative 2me divided by h bar. And L is equal to the square root of 2m over h bar squared multiplied by 32 h bar squared over ma squared plus e. There's a lot of square roots here. And once again, this technique we're using is getting pulled straight out of the section talking about the finite square well. So reread that if this seems like I'm pulling this out of my ass or just it's coming out of nowhere, because it's not. We're using the direct derivation followed from the finite square well section. And I'm going to say, okay, since there's so many square roots here, I might be interested in what the square sum of these two terms is. So if I write out k squared plus l squared, that's going to give me negative 2me divided by h bar squared added with 2m over h bar squared times 32 h bar squared over ma squared plus e. And if I add this all together, this is going to give me negative 2me plus 64m h bar squared plus 2me, all divided by, let's see. Actually, you know what? This is a little bit of a messy way to write this, so let's rewrite this. This is going to be negative 2me over h bar squared plus 64 over a squared plus 2me over h bar squared. So these two terms cancel. The final result is 64 over a squared. And this is interesting. So if I then move the a squared over to the left, I get k squared a squared plus l squared a squared is equal to 64. Or k squared a squared is equal to 64 minus l squared a squared. And the reason why I'm isolating k squared a squared is, if you remember here, if you look at this, there is an LA term. So we might be able to sort of solve for LA in terms of KA. Let's see. Going back to this, I can take the square root of everything. I can write KA is equal to the square root of 64 minus L squared A squared. And then at this point, it's going to be possible to get KA from our transcendental. Because if you look at our transcendental, which is this, if I divide by, say, cosine of LA, then I get negative K. And actually, you know what? I want to get K on its own. So I'm going to divide everything by sine of LA, in which case I'm going to get negative K is equal to L times cotangent of LA. And if I multiply both sides by A, I get negative KA is equal to LA cotangent LA. And once again, if this feels like I'm doing this just randomly without any logic, this is following the derivation from the finite square well exactly. So look at that section, look at how that wave function is solved in that section, and you'll see that we're actually doing the exact same thing we did in that section. So at this point, then I can replace Ka with this term. So then what I get is La times cotangent of La is equal to the negative of the square root of 64 minus L squared A squared. And then at this point, I can move the negative over to this side, negative cotangent LA, and I'm going to move the LA to the other side is going to equal the square root of 64 over L squared A squared minus 1. Where I move the LA into I move the 1 over LA into the square root. And at this point, we're basically done, because remember, we're trying to find valid values for the energy, and at this point, we've found a transcendental equation in terms of L. We can graph this out, find the valid values of L, and that's going to give us the valid values of E. Because remember, L is equal to this thing, which has E inside of it. So if you took this onto Desmos, and you graph this using LA as the variable, you would get something that looks like this. And very clearly, we see there's 3 valid values for LA, which in turn implies that there's 3 valid values for energy, so therefore there are 3 bound states for this system. 3 bound states. And with that, we are done with part A. Okay, part B, we're set that in the highest energy bound state, we want to find the probability that the particle is actually outside of the well. X is greater than A, and we're also given the answer, which is 0.542. So even though it's bound technically by the well, it's actually more likely to be found outside of the well because of the nature of the way probability works. So we have the values of K, we have the values of L, we also have the relation between B and C. Immediately, we can look at our graph. So if you did this on Desmos and actually graph this out, you would find that sort of the highest energy that corresponds to like the farthest one for LA all the way over here, this solution right here, corresponds with an energy value of E3 is roughly equal to negative 0.34 times h bar squared over ma squared, roughly, because it's like this corresponds to like LA is roughly equal to like 7.96, and we know what L is equal to. So if you plug everything in, this is going to give you that E3 is roughly equal to negative 0.34 h bar squared over ma squared. Next, let's write out the solution that we have so far for psi of x. It's piecewise, remember? C2, or let's write this in terms of A, B, C, D. B times sine of Lx when x is between 0 and A. And then we have C times e to the negative kx when x is greater than A. And then we have this relation between B and C. So let's rewrite everything in terms of B, in which case C is going to equal B times sine of LA times e to the ka. So that means we can rewrite psi of x to be equal to B times sine of Lx when x is between 0 and A. And then we can rewrite C as B times sine of LA times e times ka times e to negative kx when x is greater than A. Rewriting this a little bit, we can get that this is equal to B sine of Lx, x between 0 and A, and then B sine LA e to the k of A minus x when x is greater than A. And at this point, it's just a matter of plugging everything in and normalizing. So let's just set this up real quick. Honestly, it's not really worth solving it because of how annoying this is, and it's not really involved in physics. This is more of a mathematical exercise at this point, but let's write it out. So this is going to be, let's see, B times sine of x times square root 2m over h bar squared times 32 h bar squared over ma squared, and then add our value for e, minus 0.34 h bar squared over ma squared. H bar squared over ma squared. Let me just verify that that's true. Yeah. Take the square root of this entire thing. And then at the bottom, we have b sine, once again, but this time with a at the front instead of L. So a times the square root of 2m over h bar squared times 32 h bar squared over ma squared minus 0.34 h bar squared over ma squared, multiplied by e to the power of k, which is going to be square root of negative 2me over h bar squared. So let's write this as exp of, and let's do a minus x at the front, and then the square root of negative 2me over h bar. So I'm going to pull k down so I have something to copy. And you know what? I'm going to pull the h bar down here as well. And then we have the square root of negative 2m multiplied by e, where e is equal to this. So the negatives cancel out, actually, and we get 2m multiplied by 0.34 h bar squared over ma squared. Let me just double check that that's correct. H bar squared over ma squared, yeah. Okay, so obviously there's some simplification that we can do. This is between 0 and a, and this is when x is greater than a. Immediately, we see that these two fractions share a common denominator. So we can do 32 minus 0.34, and I'm too lazy to do that in my head. It's going to give us 31.66. So we're going to get, at the top, we're going to get b sine of x times the square root of 2m over h bar squared times 31.66 times h bar squared over ma squared. And we can simplify this even more, realize that the h bars cancel, the m cancels, and we get, instead, this becomes b sine times, let's see, x over a times the square root of 2 times 31.66, which is going to give us 63.32. So this is what's at the top. At the bottom, we're going to get b sine. And here it's the exact same thing, except it's an a instead of an x. So we just get the sine square root of 63.32 times the exponential exp to the power of a minus x divided by h bar multiplied by, let's see, so the m's cancel out. We get an a at the bottom. And then we have an h bar at the top, which cancels out with the h bar at the bottom. And then finally we get the square root of 2 times 0.34, which is 0.68. And if we rewrite this, we get, let's see. So this is going to give us b sine, and you know what? There is actually a lawnmower outside, so give me 1 second. I'm going to change my recording. Okay, lawnmower stopped. Let's keep going. So we get b sine of x over a square root of 63.32, and I'm just rewriting this to make it neater, times b sine of root 63.32 times e to the power of, and I'm going to rewrite this a little bit. I'm going to move the a in. I'm going to add a negative at the front. So I'm going to get, let's see, this is going to be negative root 0.68 multiplied by x over a minus 1. And this is between 0 and a, and this is when x is greater than a. And at this point, we can just solve this and normalize it and recognize that the probability that we're looking for is going to be equal to the magnitude from a to infinity of psi squared dx, which is obviously going to be the integral from a to infinity of b squared times sine squared of the square root of 63.32 times e to the negative 2 root 0.68 times x over a minus 1. Because remember, when x is greater than a, the only equation that applies is this bottom one. The only thing we have to do ahead of time is we have to normalize this wave function and solve for b. So to do that, we say, okay, the integral from negative infinity to positive infinity of magnitude psi squared dx is equal to 1, which implies that the integral from 0 to a of b squared sine squared times x over a, and I forgot to do this, square root 63.32 dx plus the integral from a to infinity of b squared sine squared root 63.32 times e to the negative 2 square root 0.68 times x over a minus 1 dx has to equal 1. And at this point, we just solve for b and we plug it up into this expression right here, and we find what this expression is. And you'll see, if you actually do this all the way through, you'll find that it does indeed actually match the answer of 0.542. You know, this integral right here is equal to 0.542. And I'm not really going to bother to actually do this integral the full way, because this is just kind of a trivial integral to do. You know, this is straight up just, you know, a sine integral, a sine squared integral, so we can use sort of trigonometry and law of like double angle and whatnot to like redefine this, solve it that way. This expression, we do the same thing. And at this point, you can just at this point, realistically, if you were taking this for a class, you would be allowed to just plug these into integral calculators and do them that way. So I'm going to leave it here and say that this is just how you set it up. You can put it into an integral calculator. If you want to practice your math, you can do that. But this is the resulting answer that you should get, which is 0.542.